what I've got for us today, really, because I want to talk about microcontrollers for this whole series. And you say each of our sessions, which I've put together, more than half have been suggestions from you lots of what you might like to see. So I'm trying to put a bit of a narrative around that for us. So what I thought was would kick off with, it's almost like an overview of microcontrollers, I should say. So, we can look at the platforms, some of the parameters of around different platforms. We'll have a look at clocks, resetting, programming, and then just a little bit of debug at the end. So I've got two platforms here. These ones we're going to use. This one here is white one. This is the mbed Nucleo board, this white one here. And this is based on the ARM Cortex M range. And the ever popular Arduino, which is made by Microchip, or you might see Atmel written on them. Atmel's owned by Microchip. So I'm going to base everything we do this series around these two platforms, which you can buy off the shelf, or probably order, probably. Mapping doesn't exist anymore. Usually these things cost about sort of, between about 15 to 20 pounds each. They're not that expensive. So as a little overview as to what you get for your money for a microcontroller. There we are, hopefully you can see that. So I've just done a little quick breakdown. Pretty much you'll find these sort of features on every microcontroller going, without exception.
Are we supposed to be looking at some kind of PowerPoint or something?
No, this is a printout. How do you mean?
We're looking at the, we're still looking at the microcontrollers.
Right, has the picture frozen?
Yes, it's still the first page.
Oh, didn't I say? Right, hang on a second. Bear with. Let's see what we can do here. Right, so something has frozen now. I said this would happen. One moment, everybody.
I was set up to do a demonstration for the entire company today. I had the equipment under test all ready and all set up and queued, ready to do the right demonstration. I had Teams set up on the phone, ready to go. And it is at that exact moment as I go live that Teams decides, you know what, I don't like fingerprint ident anymore. I need you to go through the whole authorization rigmarole, including text message. Thanks, mate.
Right, all right.
Happens to worst of us.
Right, hang on, talk about yourself for 2 seconds whilst I try and work this out again. Right, let's just see if this will reshare. Oh, right, what's happened there? Have you got a different? Right, okay. Tell me if it goes slightly wrong. I've got a green box around the screen here, so fingers crossed. Right, so yes, like I say, if it goes wrong, pipe up. Otherwise, I'll assume everything is brilliant. Right, now then, where were we? So, as I was just saying, these two microcontrollers we've got here. So we've got an ARM one here. This is the ARM Cortex range. And this is the Microchip Atmel AVR range. And everything we do, I thought we would concentrate around these. So first things first, what do you get for your money? Right, you generally do get serial interfaces. And there will be a whole session around serial interfaces. So this is going to be a little bit of a glossy overview just now on these. There's one here called I2C or I2C. I think this was one invented in the 1980s by Philips. There's one called SPI, which stands for Serial Peripheral Interface. I think that's invented in the 80s by Motorola. And there's one here called UART for Universal Asynchronous Receive Transmit, bit of a mouthful, which again has been around since God was a boy. And generally you will find, as when we play with these things, that every sensor you can buy as a chip or memory device for storing your data they will 99.9999% will either sit on the I2C bus or the SPI. There's no other choice really. And that's why you'll find them on just every single microcontroller. As I say, I've got a whole session based around this, so it's just a bit of a glossy overview on that little corner of the page.
I've heard of one called One Wire. Is that a variant of one of those?
Oh, One Wire is often used. It's what One Wire has the clock and the data on. One wire. Can you believe? In fact, it's even powered off the same wire. So it'll power the chip and it'll send the data back and forth. Usually they're used for things like security chips for IDs. An ARM chip, for example, has a unique number, like a registration plate inside the chip, which you can read out. AVR chips don't have that, so you can actually have a little wire, a small chip that just uses one GPIO line to power the chip and get the clock and the data off on the same wire.
I've used One Wire. As Phil Harding put it, it's a right royal pain in the arse.
I imagine, I absolutely do imagine that it is so, yeah. And UART is used pretty much exclusively for just about all communications. We'll talk about at the end a little bit, and debug, we use the UART. Again, I've got a whole session on debug, so it's a bit of an overview on that for us this evening. And then just moving over to the right here, general purpose, digital and analog I/O, which again we've got on these boards. You know, we've Arduino put the analog in this corner here, and digital up here, and this one here is power. We'll look at that in just a second. And of course, the analog can either be analog to digital converters, which is what ADC is, and digital to analog and analog to digital for getting analog signals from the real world into your into your microcontroller. So that's just a little bit of a glossy overview of the sort of things that you'll find on every microcontroller without exception. And how you want to use them is going to very much depend on your application. So I've just printed off here. Hopefully the picture screen hasn't frozen. Shout if it does. So this is just the AVR chip from Microchip. You can see they've actually grouped them into analog here and digital on the right-hand side. You might not be able to read that, but they've got the I2C up here in gray where I'm pointing. The SPI communications they've put on this corner here, and then the UART they've put down here in the bottom right-hand corner. And then the other pins are digital pins. And what I've noticed over the years is that this pinout has very much become a bit of a de facto standard. And you'll find all sorts of little plug-in boards and development boards which will adhere to this pinout. So whether you're using the Arduino board or you're using a ARM chip here, or even if it's Texas Instruments or anybody else's, NXP, of course, they'll all pretty much adhere to this pinout regime. So you don't have to think, I must use Arduino. That absolutely today, and hasn't been for a number of years, that absolutely is not the case. And just to complete for the boards that we've got in front of us, I've got the pinout here for the ARM Cortex, called a Nucleo board from ST. As you can see, they pretty much followed exactly the same theme. They've just got a few extra bells and whistles chucked in. They've got an extra serial port that you can play with. There's an extra I2C pins. So they all seem to follow the same sort of general principle. And then depending on who the vendor is, let's add a few extra bells and whistles for you. Right, okay. Trying to keep to time a little bit. So moving on from general platforms, and so I have the Nucleo here one and the Arduino because in my personal experience, these are probably the two easiest to use and the ones which I found as being the best applications and demo code for making your own devices. So which one's better? There's a question. So what I had a look at was a comparison between the two. And so I've got just a couple of slides there, which will just, which one do you want? So we've got the AVR, which is the Arduino, and we have the ARM ST32K on the Nucleo board. And if you look at it, obviously there's like so many different chips out there, but this is just a general flavor of what you might get for your money. So if you were to look on the face of it here, you'd say, well, the ARM chip clearly wins hands down. It's clearly got, you know, for the two chips are off the shelf we can play with, there's clearly more flash, it's a lot more memory. There's not a huge amount of EEPROM in an ARM chip. Slightly narrow operating voltage. But hey, look, it's got two I2C ports, two SPI, at least for this one here, and sort of, you know, two UART ports. So you'd think, wow, that's almost a no-brainer. Why would I bother with AVR? Well, guess what? There's probably a very good reason I want to go AVR. And in my view, I think the main one at the moment, if anyone's been following the news since March on the semiconductor industry, as you can see, based on availability, you can't buy ARM chips at the moment. So I guess it's a bit of a moot point, isn't it, really? If you can't buy it, there's no point worrying about it. But, you know, joking aside, they are versatile chips, the ARM cores, no doubt about it. You know, ARM has sold billions of, you know, ARM core licenses worldwide. But I think for the AVR side, personally, I think the support is probably much better for Arduino and demo codes and literature. I think it's definitely better for the AVR side of it. So if you're more of a learning hobbyist, I think stick with an Arduino board personally. You know, the cost is about the same, and you can certainly buy a heck of a lot more of them at the moment. These are figures as of yesterday, since I was having a bit of a route around. Yeah, and just the last thing here to share with you is one of the really nice things about ARM chips that you won't get on a microchip AVR is if you pick the family of chips correctly for ARM, you will find that between like the M0 Plus all the way through to the M4, they're pretty much footprint compatible. So the board we've got here, this is the same board they use for all these chips. So you could actually desolder that and just drop in, you know, a bigger chip. So if you were designing your own electronics, you could, and you realized that you needed more power, you could actually just change the chip without having to change your board. And I think that's worth something. Of course, you can't buy these at the moment. That's awkward. But what you can do if you're doing development is the Nucleo boards, which is what these are, because I have checked, you can still buy all of these. So if you're doing some development work, it's not really going to be a problem. If you want to make a product and sell it, yeah, you've got a problem. And you know, just on that point, I have been, say, following since March. You still hear me?
How are you? Sorry. I've been calling you.
No, I'm good, thank you. Sorry I missed your call because I was at work. I finished work now. But yeah, I'm in Cambridge today. It's tomorrow. I'm going to London.
Right.
Okay. I wanted to just pass you.
Emma, can you turn your microphone off, please?
In case something happened, you have my card and you show my card to them.
Your payment card?
Yeah.
Emma, could you just turn your microphone
I
off?
don't think it should be. It just says bring ID. I think it should be fine.
Maybe her.
Let's just take. I want to be sure. You know, I don't want to again something happen with these people. You know.
Oh, right. Okay, I can hear Emma. I'm not sure if anybody else
I don't think it should be a problem, but where are you
Stephen,
now?
you
Are
might be able to
at
boot them
home?
if you're
Yeah, I'm at home.
homeowner.
I can come and drop it somewhere convenient.
Right. One moment, everybody.
It's not going to go. I think it should be fine. But if you want to, that's fine. I'm in town right now. Just walking back home.
Okay.
Off.
Can you send me some address or something to come like in an hour? I'm in the webinar now.
Right, hang on a second, everybody. So function lets me mute people.
When you come, you can have a look at my bike.
Right.
Of course,
Okay.
I know. Yeah.
Right, sorry, everybody, a moment.
Okay, I'll send you the address.
Do you
Sorry,
know
Deborah?
problems
Mute
like
everybody.
the brakes or?
I think it's
Yes, one moment. I just got to try and find out how I do that.
I'll bring tools. We sort it out.
Right.
Thank you so much.
Yeah, right.
Remote control
See you later.
more.
Bye.
Yeah, bye bye.
Right, Emma, do you like to mute your microphone for me? How can I mute people? I'm not sure how to do that. So I like to encourage questions. Can you all still hear me now, okay?
Yeah, I can still hear you.
Mm-hmm.
There we go, there we go. We just enjoyed someone's telephone conversation there, but we're all okay. Right, okay, I like to encourage questions. So, I don't like to mute people. I'll have to work out how to maybe do that another day. Right, okay, back as we were, eh?
Right, I've got a question.
Yes.
When is it worth using a development board, and when is it worth using the bare chip?
Oh, very good question, John. Right, okay, so if you're doing early stage development work, if you're trying to decide what chip you want to use, then I would probably say get a development board. If you want to do ARM stuff at the moment, definitely get a development board. If you've gone some way down the road and you're happy with your design and it's all working, then sure, and you feel confident, then I would probably just, design the board around the chip. I mean, for me, for example, I've got a library of designs that I'm very comfortable with, and I've used them many times, and I know they work perfectly. So in some applications, I'm very confident to go straight for the chip. So, John, it depends on how comfortable you are, and of course, what the application is and how well you believe the chip will do the job.
Well, for example, I'm at the early stage of a project which I know is within scope of the basic Arduino chip. And I'm thinking, since I'll eventually put it on a board with that chip, is it as easy to do it with that chip in a breadboard, or is there an advantage to using the equivalent Arduino, a Nano, on the breadboard?
Well, I think the only advantage of basically using a development board is it is quick, it is easy, but I mean, don't forget that all these development boards, like the ones we've got here this evening, they are pretty much just a chip on a board. They don't really, they don't really bring anything else to the party.
That's what I was thinking. So
I will say that it's
just for the chip.
I will say that if you're using a dev board, you don't suffer the dislodging wires problem that you get when you're breadboarding. So you can make up plugs that go into the sockets on the dev board, and those things hold nicely. And you can basically create something that's nice and mechanically and electrically stable. Also, when you if you're wiring stuff up on the breadboard, you got loads of sort of loose wires all over the place that can take in that can get extra stray signals induced on them and so on and so forth. So you can get an electrically cleaner result with a dev board.
Yeah, just before we move on, look at clocks. One thing that I will say about using a dev board is with the Atmel chips range here, the microchip, as you can see, it comes in a DIN rail, a DIP package. A DIP is what we have here, where you can actually take the chip out and stick it into a breadboard. Whereas with the ARM cores, they are all, without exception, surface-mounted devices. So you would actually have no choice but to use either a development board like this, or design a or a custom PCB. So yeah, good question. I like that one. Right, okay. So let's have a little look at clocks, shall we? Now then, this is interesting. So clocks, almost a slightly boring subject, but it's worth having a look at this here. So it's a fairly dull circuit. It's a crystal with a couple of picofarad capacitors either side. If you look on, this is whether using any microcontroller, whoever's it is, it's exactly the same configuration. Where if you look at this one, you can see it very carefully. I'll be able to zoom in or not. Can I zoom in? Let's see if I can zoom in, shall let's see if I can do a zoom.
Second one down.
There we go. Thank you. It might be slightly blurry, but I'm sure we'll cope. Will that refocus? Ish. There we go. Right. So with crystals, when you're designing your board, say you'll always find, and it's always a good idea to put them as close as possible to the microcontroller. So when you're doing your own layout, just make sure you can see that they've kept it super close. On the microchip part, sorry, not microchip, sorry, on the ARM part, certainly with ST devices, they actually can run even without a crystal. They have an internal resistor capacitor network. So you can put a crystal on here if you want to, but when you buy the ARM Nucleo board from ST, they default to the internal RC oscillator. And so I actually did do a little experiment on this to work out, well, just how fast do they go? And so for the two boards we've got here, the AVR, this is the Arduino board, it can clock at 0.4 to 16 megahertz, and on the board here, it's a 16 megahertz clock. And on the ARM chip, much higher, but this 8 megahertz comes from an internal RC on the chip. So you don't actually have to do anything. And if you're using mbed, which will be another session, for programming these these ST ARM cores, it's all done by default, so you don't have to worry about configuring it. But the question is, which one goes faster? You'd probably like to think that the AVR going at 16 megahertz goes a heck of a lot quicker than the ARM chip. But what I found when I looked at the speed of these devices, what I found was by putting this as a square wave on here, in fact, we could probably have a look at it if you'd like. I don't see why not. I'm all for experiments if you are. Let me just swap to a different camera for you. And fingers crossed, one of these, it might be that one. Probably isn't. Maybe it's that one. There we go. Right, can you see my oscilloscope?
Yep.
Great stuff. Right, tell you what, I'm just going to power up these two boards. And fingers crossed this will work first time, because it did when I was tinkering with it earlier, but obviously it probably now won't, because that's just the way things go in my world. Right, so if I do this, right, let's swap back to the other camera in just a second for you all. Like this. One moment, people. Right, let me just swap back for you so you can see what I'm doing here, rather than looking all a little bit all cloak and daggers. Right, so what I'm just hooking up here is I've powered up my two boards. Yep. And I've put a little program into both these boards. It's exactly the same program. And it's just oscillating one of the pins like a square wave, just on, off, as fast as it will go for either using the Arduino, they call it a script program, or the mbed Blinky program. That's all that's running in these as fast as it can. And we'll hook it up to the oscilloscope and we'll see just how fast they go for the clock speed that's in them. Right, okay, so I'm hoping I press auto on there. Right, I'm going to change cameras so you can now see exactly what we've got going on here. I think it's this one here. Here we go, right, there we go. Now if I just pause that, there we go. So the bottom one in green, this one here, yep, so this green one here is actually connected to the Arduino board. And it's a program just to oscillate just one of the digital pins as fast as it can. So there's no time delays. And this top one here, this is exactly the same program running in the ARM mbed. And yet the bottom one is running on a 60 megahertz crystal. And the top one is running on an an RC, which if you look at the data sheet, tells you it's running at 8 megahertz. So I guess there must be some internal scaling up of the clock on the ARM. So the ARM is actually running significantly fast. In fact, I did do this earlier and just checked it. And this bottom one here is oscillating at 148 kilohertz. And this top one here is wiggling, I think it's about 800 kilohertz. So the top one's about, what, about 6 times faster, 5 to 6 times faster than the ARM is running 6 times faster than what the microchip is. And that's probably, I would hazard a guess, that might just be down to the environment of you know, how much fat there is and what the ARM core and the microchip is doing behind the scenes, which you and I don't get to see when we're using those development environments. So there we go. So it looks like the ARM one, if you're looking for speed, it looks like ARM might win hands down. So another one for ARM, eh? Right, let me swap back to the overhead. I like it when experiments work. Right, yep.
How stable are these clock speeds for the ones without crystal?
The International Space Station will be overhead on
In particular, temperature state.
8:11 p.m.
Yeah.
458 seconds.
Okay, 458 seconds. Do you mute your microphone, whoever's playing with that? Oh, I love it. How stable is it? I've never had a problem, to be honest with you. They both all seem to run pretty rock solid. I've done loads of work with timings, real-time clocks, and everything. You know, with the ARM core chips, you know, running off the internal RC.
I found them extremely stable and even thermally stable, which is a kind of a yeah, it's kind of a big deal if you've got a device that's going to be subjected to different thermal environments. You can get variance in the clock, but the internal oscillator seems to be pretty darn stable.
Yeah, there you go. You heard it from John.
Okay, yeah, I was thinking of the range, say, -10 to +50 centigrade. The range in a car that's in the snow or in the sun.
Again, you know, I mean, I've been using these devices for many years, John, and I've never yet experienced a problem.
Excellent. Thanks.
I mean, I have done tinkering, you know, like if you take like a freezer spray, you know, to see, you know, do you end up getting clock skew, for example? And you know, as John Green just says, is there, they really are as steady as a rock. I think many years ago that probably wasn't so much the case, but today it is. All right, so I'm going to pop these boards here out the way. I like to try and chuck in a live experiment with us when we're doing things. Right, there we go. Squeeze that out of the way. We'll keep our main event on display. Right, let's have a look at reset, shall we? This is something which I think all these boards seem to drop the ball on, in my view. So when you are resetting a board, so when it powers up, you want the thing to come up in a good known power up state. So this is sort of a timeline of what should happen, but certainly on all the development boards, this very rarely does happen. So here's a little personal gem from myself. So most resets are what's called active low. That is to say that the pin itself could either be logic high, let's say 3.3 volts or 5 volts, or logic 0, which is 0 volts, too surprising. And when we say active low, in order for that pin to be active, it usually has to be at that 0 volts or below a certain threshold. So when we power up, we really want to hold the chip in a reset mode and wait for the power to actually become stable before we allow that chip to start to do anything. Often that's achieved very easily. I'll show you in just a second, with a resistor and a capacitor. Then, and this is the bit that generally just gets completely glossed over, is you really want to be holding, if you've got other things on the board, let's say you've got, maybe another microcontroller being controlled by the main microcontroller, or this Arduino controlling this ARM mbed. So this was the blue one, conveniently by the color of the board. You'd want to hold this board here in reset until this board has come out of reset. And you'd do that usually by using, say, a GPIO pin. So you could use one of these pins to actually be the auxiliary reset. So that would then bring your electronics out of its reset in a good known condition. Often what you see on these boards is everything's off the same reset line. And I just think that's probably really a bad design philosophy to do that. Hold everything in reset off a reset pin. When the microcontroller's out of reset, then the microcontroller controls the reset of everything else. And I've got a circuit here that will do this for you. So this is a couple of ways of doing this. Again, this is our microcontroller with this active low reset. You can get chips that do this. This is a Maxim chip here called Maxim Max 803. And this chip here will monitor the power rail. And when the power rail is stable for 240 milliseconds, don't ask me how they came out with that number, they did. It then brings the microcontroller out of its reset state. So you're in a known good stable position to power your board. You can do it quite easily just with a resistor and a capacitor, so I've put these on here. So you could either, I can't really block that out there, I could do it with the biro. There you go. You can either do it that way, or you could just get rid of that and cheap and cheerful, just use a resistor and a capacitor. It really depends on your application and how good your power supply is. That would be, I would say, would be the deciding factor. If you want this circuit and all the other notes, I'll put it in the notes, but I'll do it now whilst I remember. So I have, you can download all of these. I did also put a link. I've got, can I just do everybody? Hang on a second. Send chat to everyone. Right, there we go. There you go. So if you want to download these slides I've put together with the circuits and the notes, they're all there ready to download. So you can grab these anytime. And there's also a link on the Makespace page. So if you don't want to grab the Silicon Cortex URL there, you can just grab it later. What's the one? Oh, this is the output. So if I was using the microcontroller, it's that one there, to let's turn the exposure up a little bit. There we go. Is that brighter? So you could use that microcontroller with a very simple circuit to reset this microcontroller. Usually, because don't forget, whenever you put a chip into reset, all the pins will start to float in an unknown state. And so if you're going to have this chip controlling this chip, then it's a good idea to put a pull down resistor on here so that when these pins, output pins are floating, when it's in reset, you don't end up having everything else floating as well. So if that's floating, that pulls down to 0 volts. If that pulls down to 0 volts, that will be, say it's a 5 volt circuit, that'll be at 5 volts, which will switch on this transistor, which means that will then be down at 0 volts, all for that possibly floating. So it's another good design tip for controlling the reset. And not necessarily a microcontroller, of course. It could be anything, could be any sensor that has a reset line, or a lot of the communication chips like Bluetooth, Wi-Fi, the others, wherever they are. They've all got reset controls on them. And so that's how I would control the reset. Right, okay. Not quite at the end of this lot yet. So I wanted to have a quick look at programming for us. So there's two environmental IDEs, as they're called, Integrated Development Environments, I think it's called, something like that. There's the Arduino one, which I'm sure we all know and love. And of course, there's ARM's mbed, which is also pretty good. I've just dropped in here for you the two URLs. If you're not aware of them, you don't need to write it down. You can always get them offline, download them in the documents. But I thought it'd be just worth having a quick squiz to, if you're programming boards or if you've got your own design, how would you program them if you haven't got an Arduino board or a nuclear board where the programming setup is all built into it. So the programming the microchip, it's all of this corner, top left of the board. And for programming the ARM chip, it's all this stuff here on this left side of the board. So in your own design, you probably wouldn't have that. So what do you do? That's the question. Well, for the ARM, it's actually pretty easy. There's a couple of programming pins called, this is serial wire, data and clock, to just a header, and they call this core site 10. Let's write this here. It's called core site 10 because it's looking at the core and it's 10 pins. Not very imaginative, is it? Rather than buying it like this, you can actually buy this lot in a program module, which looks something like that. So all of this here, and it would look like it would break off, is actually just inside this box here, which you can buy separately. And then this here would actually then just map to these pins on here. And ARM have made this called, they call this core site 20 because it's 20 pins. And so that's core site 10 because it's 10 pins. And you will find you can download and you can just find out what the mapping is from core site 20 to core site 10. It is just wires, that there's no electronics in the middle of this at all.
20 is just basically the same as 10, but with a bunch of extra trace wires.
Yeah, cool. Pretty much. Again, you know, there's no great secret to these things. And yeah, and if you're programming, you know, if you're using mbed, do your own design. With mbed on your own design, you can either download, certainly with the latest OS 6, 5 or 6 I've been working with recently, you can download straight to these boards without any messing about. You just press the play button with like an arrow for play. It compiles and sends it straight to the board and runs it. no dramas at all. If you're designing your own electronics, of course, and you've got the header, then you'd have to output the file from mbed to what's called a .hex or .bin file. And then they have a program called stutility, I've written here, which is connected to this box of tricks and then to your chip. And you can just open the .hex file. And again, you just connect to your target, which is your chip, and just upload. And it's as simple as that. There's no real special secrets, piece of cake, no dramas. For the Arduino, you can actually use the Arduino board to program a chip on your own board. So you're talking about, if I wanted to put this on a breadboard, well, here's one here. You can actually use the Arduino itself as a programming module. And I wish I knew the name of it, should have looked it up. I think on the Arduino program suite, there is a program which you can use in order to make the Arduino Uno board a programming module. There are some notes, I think, on their website to enable you to do that. Again, it's really very, very easy. You have a special program in here, which they provide on the script. You will find it somewhere in the menus. And you just a few wires. So if you design your own circuit, which I've done here for us, I've kind of kept for my own sanity to a similar to the Coresight 10, just for my own sanity. It's very similar, but there is no rhyme or reason or script for that. And that's all I had to do. You're just connecting a few wires up. So it'd be very easy just to put the microchip and a header in your own design and run a program to it. Not hard at all. If you were having problems, well, hey, look, you can always just unplug this chip from the board and stick that on your own. That would work. Right, okay, so last thing on my list for you this evening is I wanted to have a little look at debugging. Again, I've got a whole session on this, so this is going to just be a little bit of an overview on some of the debugging things that I put into my electronics and what might be of use to yourselves. Because when you look at these boards, they come with precious little debugging capability, and the IDEs have pretty much next to nothing. So I always bang on a few LEDs. Okay, it helps me see, if I've got a loop going on, if I've got something going on, it's almost just an I'm alive flashing LED at the end of a process, just so I know the thing hasn't hung. So, and if I want to see various events, LEDs are a dead easy way to do it. Piece of cake. Or keys. Again, these IDE programs that we're talking about here, you can't really halt the program at any point. So you could actually put a loop in your program just to stop and then wait for a key press in order to carry on. So I use this little trick here in order to halt the program when I'm developing, and then I can make it carry on just by then pressing a button. That works, piece of cake. And last on here on debug is the USB. So the UART, which is in the corner of these boards here, they usually put them in the corner for some reason in here. Just here where I'm pointing my pet biro. In here where it says TX, you probably can't see that, but trust me, it does. So that connects to a FTDI chip, and the FT, I'll write it here, 231XS. Make a note of that, everybody. They're about the only chip you can still buy for UART to USB for debug. So there's a top tip. And then it just connects to a standard micro or mini USB, and then you plug that straight into your laptop. And there's a couple of programs you can use. I've read a couple here for you all. Real Term, you can download, it's a freebie, and Putty is another freebie. So you can then have various bits of text coming out of your program of what your microcontroller is doing, and you can have it coming up on the screen so you can start to see exactly what your design is up to. And this is the actual screenshot from the real-term Apple program. Again, it's completely free, no charge for it. Just type that into any search engine. This is pretty much what it looks like. And that's about it. I think that really is quite a lot for an overview. Questions? Anybody? Anything you want me to comments you want me to go through again for you?
Could you please say the name of the programming device for the ARM board?
The programming device is called ST Utility. If you go to the ST Microelectronics website, what did I do with it just now? Yeah, you'll be able to download it.
Sorry,
I think you may mean the hardware device. That's the ST Link.
Oh, right. Sorry. Yes. So there we go. Written on the back here. If you can see that, okay, you can write that down. ST Link V2. It's about £20.
And are they well supported in terms of? So I've been able to persuade the chip on an Arduino to kind of accept programs via an Arduino. So I've accomplished that, but I've never used one of these ARM chips. Is it? Would you say it's tolerably well supported if I were to purchase one of these ST Link things? Small amount of support in terms of how to wire it up.
Reasonably. I think the Arduino is much better supported, if I'm perfectly honest. But I also think that using the ARM ST stuff is very, very straightforward, particularly if you're using ST Utility. The one point which you need to pay attention, this is a default, is you might not be able to read that, but I've just circled there the address OXO, and there's 8 and many noughts. So with the ST Utility, it'll have a default address to load the program to, which you don't really want to mess about with, because if you change it, you'll probably find nothing will happen when you switch it on.
Right.
But it's, if you look at the mbed, you can download, again, that's totally free from ARM, mbed, and I think ST have done a very fine job. It's 99% okay. I have found there are a few quirks with mbed where things clearly have not been properly coded, and there are some bugs, which you probably won't find with Arduino. For example, I've had problems with I2C not working, where some of the ports on the I2C are clearly not coded. So if you're going to use mbed, here's a word to the wise, whilst they do bring out every single pin to these headers, I'd be inclined to stick with the Arduino compatible, one for a better phrase, first, because these will absolutely work. Whether the rest of them do or not is another story. And that comes back to John's question earlier, should I use a development board? If you're going to use something like mbed, I would probably start with the development board, because you'll be able to prove out how much of it they've actually coded.
You also don't need to buy an ST Link because you've got one on board anyway.
Yeah, as I was saying, this entire lump here is in fact this.
And in fact, when you're tired of that board and you're about to throw the big part of it in the bin, snap off the other bit, because that row of pins at the bottom, row of about 6 pins there, that's the ones. That's basically if you can make up a little Molex single pin row plug and wire it to a Coresight 10 header, bingo, that's all you need to to drive some other board or to drive your own board.
Yeah.
Thank you.
Comes for free.
Yeah, my honest appraisal is ARM mbed, and Simon Ford, actually, one of Makerspace's own, is one of the founders.
Mm-hmm.
I would say they've done a pretty fine job. What I will say I'll just add a caveat to that, is their latest embeds, OS 5 and OS 6, there's a lot of that is not compatible with the code for the earlier embeds. So, by way of example, this is a pretty good book. I can put it under the camera actually, can't I? There we go. So this is a fairly decent book for the embed. You can get this off Amazon. I can't remember how much it is. It's been very much written around this chip here, which is the NXP chip. And I think a lot of the early development was done on mbed using the NXP, and this chip is now completely obsolete.
The NXP 1768, I remember it did, happily.
There you go. You can't buy the chip anymore. They've obsoleted it. And so, you know, I think a lot of what you'll find with a lot of the early embed stuff works brilliantly with the NXP. And when you migrate to some of the other chips, you'll find that things fall over very slightly. So, and of course, if you go from what's like some of the early embed stuff, and you'll find that some of it's now being deprecated and is incompatible when you migrate to their latest embed OS 5 or OS 6. So you'll have some rethinking to do, because some of the things that you had in your code have broken. But there is support online. If you have a dig around online, you will find what you're looking for. For example, so I've had this in the last 2 weeks with the UART RX got deprecated. My program worked perfectly until a week and a half ago. And then it just stopped dead in its tracks and I couldn't get it working again. So I moved to mbed OS 6. And of course, some of my code for the UART was no longer valid and it crashed. So I had to work out exactly what were the magic runes to make this thing work. So it hasn't been all peaches and cream, I'll be honest.
It's worth mentioning that you don't have to use mbed OS if you don't want to. You
No,
can go in and do it hardcore and do it from bare metal up instead, which is kind of my preferred method. But you know, I'm kind of used to that stuff.
Yeah, you know, at the end of the day as well, I completely agree. I don't think it really matters what environment you use and what language you use. It's whatever you are personally comfortable with.
Absolutely.
Well, I guess I'm not experienced with using microcontrollers. I've done quite a lot with Arduinos and stuff, but the idea of just buying a raw, what I would like to be able to do is buy a raw microcontroller chip that serves my purpose and stick it on my own custom board. That's my goal. But I'm kind of aware that Arduino in particular have done quite a lot of simplification work to make one's life easy. At the moment, I've just started trying to write some code for a Nordic board, and I found in the broader code a file whose purpose I've got no idea about, but it looks like some kind of setup file, and it's 10,000 lines long. And I'm sort of imagining that if I buy a raw chip, then I'm in some way responsible for making sure that this 10,000 line setup file is correctly tweaked.
I bet dollars to donuts there is some little utility somewhere that automatically generates that file. So you basically in probably in some kind of graphical environment, you set up your clock chain and you set up your peripherals and so on and so forth and tell it, go make me the file. And it makes you the file, and you never actually edit that file yourself.
I've no desire to.
Don't blame you.
Something else which I'll owing to the world chip crisis, and you can't buy ARM chips anymore. And trust me, there is nothing. The cupboard is bare. But you know, with the AVR chips, they seem to be holding their own, which is almost a good thing. But what I will say is some of the AI stuff which I've been writing. Again, I've got a session on AI coming up in a couple of months, which we'll use the Arduino and the ST chip for. I had my original AI code for doing some stuff for vibration sitting on the ARM M4. And I think, it was running, I think it used something like 8K of RAM, and it used, I think it's about 50K of flash for the program. Now, of course, you couldn't buy the ARM chip anymore. So I thought, okay, how can I do that on the AVR? The AVR's got 32K of flash for your program and 2K for your RAM for your data. So I had to rethink myself, how can I get 8K into 2K? How do you do it? And I've done it, I'm pleased to say. I thought, how did they do it in the 1980s? We had BBC Micros and Spectrums with hardly any of this at all. And yet we still had, Jet Set Willy and Pole Position, Defender, and Elite, of course. So I think I'll be honest, I think using something like the Arduino AVR, it'll make you a lot more resourceful in your coding on the microcontrollers, for sure, because think, how can I get all that in? And it's possible to do it. The way I did it was with the memory. You have like decimal numbers like pi 3.142. It's called a floating point, which uses quite a lot of, I think it's about 4 or 8 bytes, which is quite a lot. So I actually converted that point number to a round number. So just multiplied and got rid of some of the numbers. So 3.142 became 314, for example. And then I stored that as an integer. And so I'll convert it to a floating to do the number crunching, and then put it back to a whole number integer in order to store it. So I think it'll force you to be a lot more creative in your coding using an AVR than what you will be, because I think the kids today have got a little bit lazy with their programming and they just go and get more memory. Well, it's not really an option in a microcontroller. You're very constrained on memory to start with. And so when you start going to, the microchips, certainly with what's available, obviously you can buy bigger ones. Well, you can't, obviously, but when you can, that you may have some bit bigger options that you can go and get. But for where we are, I think for the next year, I think I would probably stick with the Arduino for the next year, if I'm honest, because you can at least buy that.
I had a specific project for which I needed a real-time clock, and I didn't want to, if I could avoid it, I didn't want to purchase an additional real-time clock. I was interested in microcontrollers that had a real-time clock already in them, but I didn't even...
Well, in the ARM chip, in fact, I've been doing this the last week. Actually, today I was tinkering with the RTC. The ARM chips actually got Unix time inside. If anyone knows what Unix time is, I learned this 2 weeks ago. Unix time is time in seconds, and the date starts from, don't ask me why, the 1st of January 1970.
The epoch.
Yeah. So that's Unix time, and yeah, it is all built into the ARM cores. I don't know if it is inside, and if there's anything like that inside the Atmel. I'm really not sure. I haven't looked at that yet.
The ESP clock starts at that same epoch as well.
Oh, is that right?
Yeah, I discovered that the other day when I was playing with time libraries.
Yeah. So I've had it running today, and also in the ARM stuff, there's certainly on the mbed OS 5 and 6. There's actually just commands where you set up the Unix clock with however many seconds from date 01/01/1970, and then there is a command. I think it's called ctime open bracket and then whatever the Unix seconds time is, and then it'll actually convert it to today's date and time for you in one line.
A word of caution: if you're expected to use your project beyond 2038, Unix time ain't good enough because it overflows at that point.
Yeah. There's so there's only 2 more leap years to worry about for anyone doing a perpetual calendar based on Unix time.
Unless the smallest microcontrollers are 64-bit by then.
That's exactly what will happen. They'll just slap on a few more bits and carry on. That's exactly what they will do.
Oh, yeah.
Can I just check that I've understood that correctly? I can buy a chip that's never been connected to anything, and it still knows what Unix time is.
No.
No.
You have to sell it.
Right. Okay.
Yeah, fortunately, that doesn't work on Magic. You've got to set it, and obviously you'd have to keep it powered. In which case, I mean, they do have certain ARM cores. There is a it's called VBAT pin. If you look at the data sheets, Andrew, where you can just put a battery on, and then that'll maintain your RTC when the rest of the device is powered down.
Okay. Oh, right. Okay.
And I presume it persists through resets as well. I've not tested that with mine.
Yes, it does.
So if I don't need the date, I just need the time, I could lie to it and tell it that it's 1970.
Absolutely, yeah.
Yeah.
And then it'll carry on going and for another 68 years.
Yeah.
It looks like it, doesn't it? Happy days.
Yeah.
Yeah.
If you just want to time something, the Arduino has all you need. It keeps the number of milliseconds since it was turned on. So you can work out from that how long everything is going on. So once you set the time, as long as you don't power it down, it's got everything you need to do a time, but it's not connected to a crystal. Usually the real-time clocks have a separate crystal so that the time is much more accurate over a long period of time.
Yeah, it's usually 32 point something kilohertz. The other as well thing, Andrew, is if you do use an external chip for the real-time clock, you'll probably find some which will draw a lot less power current than what's running inside, say, the ARM core or the microchip. You'll get them down to nanoamps. So then you can probably then have your backup, say, a supercapacitor, and it'll last significantly longer before it sort of draws its last breath.
If you're just building hobby circuits, a lot of the real-time clock modules come with a kind of holder for a coin cell.
Yes, exactly.
It'll keep the time for a few years. I mean, it may not be incredibly accurate. It's one of the nice things about the ESP Wi-Fi enabled microcontrollers is that you can set the time from the network if they're connected to a network. So I have mine just kind of pick up the time from my Wi-Fi network.
And yeah, and just one last thing, Andrew, to bear in mind is if you're using a coin cell to power the RTC, on a microcontroller, and you want to do battery monitoring, and you're thinking of wiring the battery to one of the ADC pins on the microcontroller to monitor the voltage off the battery, you're better off going via using a op-amp, because the op-amp will draw a lot less power from the battery than the ADC port will on the chip.
Oh, I see. It's good tip. Thank you.
Yeah, we've learned that one from experience.
So the ADC pin actually, the analog pin on the microcontroller actually sucks power out of the battery.
Yes, it's quite a bit. And saying if you do just wire your battery to it, thinking that'll be cheap and cheerful, you'll probably drain your battery very quickly.
Interesting. Yeah.
Top tip.
You could also get MSF receivers to pick up the radio time signal if you wanted to set it automatically. I think you can get one for the Arduino, for example, and a library to go with it. The 60 kilohertz one that used to be at Rugby, it's Hanthorn now.
Another way to get extremely accurate time if you need it is to have a GPS chip on there.
which I suspect is quite a lot more power than the MSF one.
Yeah, you only need to turn it on kind of once a day to reset the clock.
Yes, true.
So look, ladies and gentlemen, it's 20 to 9. What I'd like to do is draw us to a close for this session, if that's all right with you. Note for your diary, next event is Wednesday, the 3rd of November. Same time, same place. It's possible this might happen next year. I might see about moving it to the classroom at Makespace, possibly, if there's interest in that. Depends what people would like, if they'd like to do that.
Can I just vote for online? I'm based in London.
Oh, okay. Yeah. Well, it may be sort of a hybrid. Although my experience of trying to do hybrid live and online is they don't work very well. Sort of I'll be off camera or something won't quite go to plan. But at the moment, I'm planning on keeping them online at the moment. If that's what work, if that's what people want, then that's what we'll do. I think that's the fairest way to say it. The next one.
Steve, someone was asking in the chat the titles for the provisional titles for the 12 sessions for this coming.
Right.
Yeah.
So they've all the sessions are all up there on Meetup already. They're all up there. So yeah, there are one other 10 months provisional titles, please. They're not provisional; they're already up there. The next one is transistors. I can tell you that now. But yeah, if you just go to the makeups, I can't remember what they are off the top of my head. But say if you do look on the Makespace page, get my teeth in. You'll find that all the dates are there, yeah, it's all being mapped out for the whole year already. So go and take a look, and I might be able to then not have to try and remember what it is I wrote down for them all. But anyway, should we all go have a cup of tea?